Okay, so can you see my screen?
Yes, we can see your slide.
Okay, thank you. So I'm gonna use my laptop tablet to give a presentation because I need to write something on my slides. So okay, let's start. Hi everyone, my name is Guanren Wang, and today's topic is a brief introduction to optimization on manifolds. Okay, I'm a graduate student from National Taiwan University. Okay, so here's the outline today. First, I'm going to introduce what is manifold without very rigorous mathematical construction, and I'll try to give more intuition behind the manifold belong. Yes, and then I will show how to do gradient descent on manifold. So everybody knows what is gradient descent, but when we change our spaces from Euclidean space to a manifold, like an abstract manifold or a sphere or something like that, how can we do, or how should we do gradient descent on manifold? And then I'll discuss some function classes on Riemannian manifold. So the word Riemannian here is remain unclear now, but I will introduce what it means a Riemannian manifold is later. And the function classes just can think of as a traditional convex optimization analogy to the Riemannian manifold settings. So in traditional convex optimization, we have convex function or smooth function or like strong convexity or something. And in the settings of optimization on manifolds, we also have these things. And finally, I will give a convergence rate of the gradient descent on manifold. And I will not prove because it requires more knowledge about this topic, and which is yes. Okay, so first, let us consider a constraint optimization problem. Say we have a objective function f. Oh, sorry. We have an objective function f, and subject to we are going to minimize this f and subject to the constraint set s. And this is a typical formulation of a constraint optimization problem. And there are some algorithms can solve these problems, like the famous one, vanilla gradient descent, or we should say a projected gradient descent, because our iterate after updating each step, our iterate should be stay in the constraint set. So after we update the iterate, we need to do a projection. So maybe I should say projected gradient descent to solve this problem. But there are some maybe thorny issue to this problem. For example, if the set S, the constraint set S, is complicated, so we cannot easily compute it, or it is computationally expensive, then this constraint optimization problem might be hard to resolve due to the constraint set. And another issue might be that if we want to do a gradient descent, the objective function should be good enough. What does it mean? It is f should be, for example, should be smooth or should be convex, which we will define later. So why should we talk about optimization on manifold? Is that because if we view first, if S, the set S can be viewed as a manifold, and if we actually view it as a manifold, then it is possible possibly the issues I mentioned earlier might be resolved, but it is not always can be done in this way. But there's a possibility to solve those thorny issues. So, for example, if we don't want to deal with the constraint set S, then after we view it as a manifold, the problem becomes unconstrained in the sense of optimization manifold, because for example, if we are in Rn and our set is like, say, this set, this is a probability simplex. So this is not hard to project, but I just give a toy example. So if we don't want to project any iterate xt onto the set, say S, then we can consider it as a optimization on manifold formulation, so that this set is the word the iterate leave. So we don't do any projection. We just update our iterate using the gradient descent on Riemannian manifold settings. Okay, so but it is not a real case, because this probability syntax is a more easy set. And another issue is it is in some cases f, the objective function is not like smooth or convex, but after if we view as a manifold, there might be f might be convex in the sense of manifold. I will elaborate what it means later, but it basically means that if f is not convex, say convex, f is not convex in the original Euclidean space, and we switch to the manifold setting, and we can possibly see that f is actually geodesically or a manifold version convex. But I'm not saying that if we meet these thorny issues, we should go to consider optimization on manifold, because to choose a proper manifold is not so easy. So I just offer a motivation and introduce the settings of optimization on manifold. So here is a very simple example. Say we are considering computing the smallest eigenvalue of a n by n symmetric matrix A. So to compute its smallest eigenvalue, we can consider minimizing the so-called Rayleigh quotient, this amount. So minimizing this amount, and on the set of Rn minus 0, 0, this one, and it is equivalent to this formulation, because if we change x to say lambda x, the amount remain the same. So we can just keep our focus on the univectors, and note that all univectors is the set of all univectors is the unit sphere. So this problem can thought of as a optimization on manifold. The manifold is the sphere, the unit sphere S1, Sn minus 1, and multiplies the objective function, which is the inner product of x and ax. And here is a toy example to show that the original problem is a constraint optimization problem, and after we change the view then the problem become unconstrained. But this is again, I emphasize that this is a easy example, because when the sphere, the constraint set sphere is the projection onto sphere is not hard to compute. You just need to normalize the vector you get. Okay, so this is the first issue that optimization on manifold may help. And the second one is, as I just mentioned, in convex optimization, we hope our objective function have some desired properties. For example, the famous one, convexity. We hope our objective function to be convex, which means that for every point x and y lies in the set, we have this inequality. And this inequality basically says that the function has the shape like this or this, because every point, say y and x, we have that y f of y lie above the right hand side. This linearization of x, linearization of f at x. So the function shape is shaped like this shape. So this is convexity, which ensure the gradient descent algorithms give us won't achieve like saddle point or local minimizer, because if the function is, say, like this, then this function is not convex. So if a function is convex, then it must be it must not have local minimizer or saddle point. And another important property is L smoothness, which basically says that our function cannot varying too abruptly. Okay, my English is not good, but this is saying that if our function is if at any point y in a set S, and it is not greater than a quadratic function, then this is, for example, this is the right hand side of the smoothness. Then the function value may not be varying differ too abruptly. So when we do gradient descent, we can make proper sufficient decrease. Okay, and the last one, strong convexity helps improve the convergence rate. So if the objective function only have convexity and L smoothness, the convergence rate is roughly t 1/t. And if we have smoothness plus strong convexity, our rate might be we may have a linear rate. Linear rate. Okay. Okay. So so this property is in classical convex optimization, we want these properties, and once we don't have once we meet some cases that the objective function of those cases don't have this property, we can try to find if there is any manifold structure such that the objective function may have this property, manifold version of this property. And again, I will elaborate what it means. This property has its manifold version later. Okay, so what is a manifold? What is manifolds? What does manifolds mean? The formal definition of manifold is in here, but it involves some advanced mathematical knowledge for example, homeomorphism, or what is a open neighborhood U of X, because X is a point in a subset M, and M is a subset of Rn. So the open neighborhood here may be some issues. I simplify the the definition here, but here may have some issue. But anyway, the intuition behind manifold is we say M is an m-dimensional manifold. We means M is locally looks like Rm. What does it mean? For example, a sphere in R3 is a two-dimensional manifold. Why? Because think about us. We live in Earth, and we locally think we are living in a flat plane. So this is what you might heard from some mathematical video or something, is that it is if the set is locally Rn, and it is a Rn manifold. So a sphere is locally R2. If you fix its point and zoom in, you may figure out you may find out that the sphere become more flat and more flatter. Okay. So here's one example, and another example is the torus, or say the sphere of the surface of a torus is also a two-dimensional manifold, or a torus itself is a three-dimensional manifold, and this is the Mobius span, and this is a two-dimensional manifold. So what is not a what is not a manifold? For example, this is a one-dimensional manifold, right? Because locally it locally looks like R1. If you zoom in this part, you will see that it looks like a straight line. But so this is a one-dimensional manifold, but this is not a one-dimensional manifold because at this point, no matter how you zoom in, or no matter how you zoom in this point, you may find that there is always an intersection at this point, and this intersection cause this point is will not be homeomorphic, or will not be locally looks like R1 and not R2 and not R3. So this is a problematic point such that this set is not a manifold if it intersects to itself. So so for example, in the previous example, the sphere is a manifold, and there are some other examples. For example, the positive orthant, the set of this set, X, those vector whose each component greater than 0. So it is basically a convex cone. Okay? I draw this direction. The convex cone of this set, and this is a manifold. So there are some problems that the constraint set is this set, and this is a this is actually a manifold. Okay, so after a brief introduction to what is manifold, can we now define what is gradient descent on manifolds? Because we have our standard gradient descent in the Euclidean space, which is of this form. It says the next iterate should be the current iterate minus the current iterate's gradient and times some step size eta t. And can we do the same thing for so this gradient descent is under the setting of unconstrained optimization, because when we talk about optimization on manifolds, we are saying that we are thinking that the manifold is our whole life, and we are doing unconstrained optimization on manifold. So to do a analogy, we consider this case gradient descent on a unconstrained problem. So can we do the similar things when we considering the optimization on manifold problem? The answer is not, because here are some problems. First, manifolds are in general nonlinear. What does it mean? Say the sphere is obviously nonlinear, right? So what does nonlinearity cost? Is that we don't know what is gradient of f, because to do gradient descent, we need to calculate the current iterate gradient, right? But the gradients, the definition of gradient is this. We need to calculate partial derivative of each direction and form it as a vector. But this is because Rn is spanned by E1 to En. But for in general, for any manifold, we don't have this thing. We don't have a manifold equals to span of something, because this means it is a vector space. But we all know that manifold is a can be not any shape, but can be like curved, or yeah, like curved like this. So it is obviously not nonlinear. So we don't have such stuff. So we don't know how to define at this step. We don't know what is so-called gradient f at the point. Gradient f. Okay, so this is the first problem, and the second one is even if we know what is gradient f, so let us denote it as so gradient f is for original Euclidean space case, and this gradient f is for Euclidean case manifold manifold gradient. So this is it. When I write this, I mean the gradient of f in the sense of manifold. Okay, so even if we know what the gradient it is, we don't know how to move on manifold, because in Rn, say we are in Rn, and we have a like the initialized point x1, and then after some calculation I obtain its minus eta 1 gradient of f of x1. So I know the next point is here, x2, and do the same thing, and then we obtain more and more iterate. But if we, so this is the case in this Rn case, but if we consider a manifold, I say sphere is good. Okay, okay, sphere, and we have a point here, say it is x1, and okay, we know what gradient f of x1 is, say this direction. This is changing color. This is gradient f1. Okay, I should write it at B. Okay, but we cannot simply do this thing. Okay, sorry, we cannot simply do this, because okay, so let's say this is minus eta 1 times gradient, because this point doesn't belong to M. It falls outside the manifold. But remember, our manifold is in this sense, our manifold is a sphere, it's a -1. So we cannot directly do the calculation when we do in Euclidean space, because we don't have a linear structure. So this is what I mentioned first. Manifold is non-linear. So when I add some elements, the add is in under the sense of Euclidean space. It might fall outside the manifold. But remember, when we consider optimization on manifold, we are considering the manifold is the whole world, the iterates live. So we cannot do things like this. So we need a method to move on manifold. We need a method to move on manifold. So here is a two-man problem. First, we don't know how to define this one, gradient f, in the sense of manifold. And second one, we don't know how to move on manifolds. Okay, so I will spend some time to introduce some background knowledge to so that we can define what is gradient f and what is the move on manifolds. But before that, we can see we can take a look of the final version of gradient descent, and we will call it Riemannian gradient descent. Again, the word Riemannian will be clear later. So the Riemannian gradient descent is of the form. So you can see that this is similar to the Euclidean case. Oh, sorry, this is T. This is similar to the Euclidean case, but there are some differences. So first, what is this one? We don't know what is this. This is not it is absolutely not this function. So yeah, it is not this function. And the second thing is that yeah, we really need a gradient f, the decreasing direction. We need a direction that tell us where is the objective function decrease. So this is the first problem. This is the second problem. So so here we already know that this one, although we don't know how to calculate it, but we know that this gradient f of xt means this in Riemannian in manifold case, in manifold settings. And this one is actually this. This is called the exponential map at x. This is the exponential map at xt, but in general we write the exponential and x in below, and this is the exponential map at x, and which is just as I just said, is a method to move elements from a manifold to a direction. Okay, I will elaborate this later. Okay, so we will visit it later. So yes, so let's start to let's start to see some definition, see some concepts that we need to construct or to construct the gradient descent on manifold, or the so-called Riemannian gradient descent. So first, we are going to talk about what is tangent spaces. The intuition is very easy. For example, if we have a sphere here, then the tangent, we will say tangent plane. Tangent plane here is this plane, right? And the tangent plane here is this plane, right? So basically, the intuition behind tangent spaces is just what we think in our mind when we think about tangent plane. So given a manifold M, the tangent spaces Txm means that the tangent space at x, the tangent space of M at x. So x is a point. Wait, I'm sorry. Wait. Oh, okay. Okay. Oh, so x is a point in M, and at every point we have a tangent space Txm. So what does it mean? Here is a quite complicated definition. Says that the tangent space is in fact consists of the equivalent classes of smooth curves, but if this is too complicated, you can think of the tangent spaces as a plane that lies the plane or the space that intersects the original M at x, and the tangent plane contains all the vector, all the direction x can move. What does it mean? Okay, so let's draw this. Okay, I draw another manifold. It is a curved sphere. Okay, so tangent. I should say tangent space. So at this point x, the tangent space is the collection of all vectors that as the direction x can move. So for example, okay, so v here is v belongs to Txm, means that there is a direction and x can move along this direction. So yes, this is what is exponential map 2. So but before that, we first talk about what is tangent plane, tangent spaces. So the element of tangent space is a vector which can be used to denote, or can be used to represent a direction that x can be moved. So And a theory says that tangent spaces are linear spaces. So this tangent space is actually linear space. So in here we can do addition or constant multiplication. So if we have something, we have a direction v in here, we can do this one, and we can do this thing, e dot times v. So which means I want to go in this direction, but with smaller step size. Okay, so here's tangent spaces. So yes, the gradient of f of xt belongs to xt's tangent spaces. Okay, I will clarify this point later. Okay, so after we have tangent spaces and we know that tangent spaces are linear spaces, we can define inner product on each spaces. What does it mean? Because okay, so I draw in here. So given a manifold and a point on it, this point x has its tangent plane, and this point has its tangent plane. This point has its tangent plane, and these tangent planes are linear spaces. So we can define inner product on it, which means that the vector on the tangent plane vu belongs to txm. We can calculate the inner product of v and u, and we denote below. We denote x in the below, which means that this is the inner product on x at tangent plane at x. So for another tangent plane, say this is y, and this is v prime and u prime, we cannot do this because v prime and u prime do not lies on txm. So if we want to calculate their inner product, we should use the this y. Okay, so this means we are calculating the inner product on TYM. Okay, so why should we define inner products on each tangent plane? It's because it is a so-called Riemannian metric. So I can explain why we need this Riemannian matrix. But first, let's see what is the definition of a Riemannian matrix. The Riemannian metric is that if we can define such inner product on every tangent plane, so every x and for x, so every tangent plane we can define on every tangent plane, then and the inner product is very smoothly with x, in the sense that if we have two vector fields v and w on M, and the function x assigned to the inner product of v of x and w of x is smooth, then this means what is said, the inner product is very smoothly with x. Then such assignment of inner product is called Riemannian metric. So a Riemannian metric. So if we have a Riemannian metric, then every tangent plane of our manifold will have inner product. So what is a Riemannian manifold? A Riemannian manifold is a manifold that equipped with a Riemannian matrix. So why we need this Riemannian matrix? It is a little bit complicated. So I can say a little bit because a manifold M is a subset of Rm. But actually we can discard this Rm. We can just look at a set and its topology. So if you have heard you have learned topology before, you will know that if it is a topological space and it's locally homeomorphic to Rm, then it is a M is a n-dimensional abstract manifold. This is different from the settings we the manifold we defined before. Because the manifold we defined earlier, we need a background space, say Rn, so that we will know that what is so-called tangent plane. But in general, we actually don't need this assumption. We can just consider a set and its topology, and to check if this is homeomorphic to Rm. And if it is a abstract manifold, but it is a little bit beyond what I am going to talk about today. So yes, and why I'm talking this is why I saying this is notice that it is a topological space, so there is no distance on this space. But via this Riemannian metric, we can define a distance on this space, and this space becomes a metric space. So if you are interested in this topic, you can search for Riemannian. Just the keyword is just a Riemannian manifold. So you can see why we need a Riemannian metric. But for our purpose to construct a Green descent on manifold, we need this inner product structure just because we want to find a vector such that it can represent the differential of f in terms of the differential on manifold between manifolds. So what does it mean? We know that a differential, a given function from n to n, I'll say Rm to Rm, the differential at x is also a Rm to Rm. Yes, it's also a map. But in this in the case in manifolds, if we have a map from M to M prime, and we call this map capital F, the differential of this capital F is a linear operator that generalize this notion. So it is not a map from okay, so here I write x. Okay, it is not a map from M to M prime, not like this. It is from as I write here, the tangent space of x to the tangent space of what f, capital F map x to. So I will draw it later. So if you feel confused here, I will draw it later. So basically, if we have this differential of a smooth map, so given a map, we will have its differential defined such way, in this way. Then, because this is a linear operator, it is a linear function. So, and it is a linear function. So it is a linear function defined on its tangent space. So it's a given a function f from M to R. It might be our objective function or something like that. So it's from M to R, and the differential of f x at x, the differential of f at x is a map from txm to tfxr, and this is actually R. So so because I have a R, and at every point x, its tangent space is R itself, right? So I have a point Y, its tangent space is R itself. So this one is actually R. Okay. So the differential, this is a linear operator from txm to R. Thus, we can find a representative, a vector in a vector gradient f in txm that represents this linear function, linear map. in the sense that for every v, for every for every x in M, and for every v in Txm, this can be calculated by the inner product of such vector gradient f of x and v inner product, the inner product at Txm. So okay, so let's draw some graph too. So the differential, if we have a big capital F from M to M prime. So let's say this is M, and this is M prime. This is M prime. Okay, and here is a point X that maps, and the capital F maps this point to this point F of X. And what is its differential at X? What is dfx? It is a linear map that maps vectors of the tangent space here, Txm, or Txm, to the tangent space here, Tfx m prime. So this differential f of x is a map from here to here, and it map a vector f to a vector dfxv. So if our f is a manifold to the straight line and the real line space, then we can find that M to R. We can find that X f of X, and we can define a tangent space. Sorry for the poor drawing skill. We can define a dfx from this tangent space to R, and which means we can find a gradient f that represents this linear function in the sense of this equality. So this is the desired gradient of f in a sense of manifold. Okay. So so we basically we have so we now have the gradient f in the sense of manifold, optimization on manifold, or a function from a manifold to a real number. Next, we need the previous mentioned exponential map. What is this? As we said, it is a map that map. Okay, let me draw it first. So given the point x in M, you have there is a tangent space Txm. And what is exponential map? It is a map from the map that maps points or vectors from the tangent space Txm to the manifold itself. So given a vector, for example, V belongs to Txm, it belongs to Txm. What is exponential x of V? It is not this function. It is we map this vector to a corresponding point on the manifold. So naturally or intuitively, this should be at this point. It's like a projection, but it is not real. It is not a projection. But you can just okay. Forget about it. So given a V in Txm, you can have this point called exponential x of V belongs to M, which satisfies this condition. Is that first we let's let's look at this description. So here, why we introduce so-called exponential map, because we want to generalize the notion of x plus v, but because we know M is not a linear space, in general it's not a linear space, so we cannot do this. But we can do, what we can do is do a exponential map. So exponential map xv is basically this one. But in manifold, this is an element in M, and this is an element in Txm. So we cannot directly add them up. But in the Euclidean case, this is an element in Rn, and this is actually an element in R, a Txrn, but as we said before, this is actually Rn, so we can directly add them up. Okay, so the exponential map is the aim of introducing exponential map is to generalize such operation. And before we say what this map do, we introduce a notion called geodesic or geodesic curve. And geodesic is given 2 points, x and y, in a manifold. X and y belongs to a manifold, and a geodesic between these 2 points is a shortest path between these 2 points. So, for example, if I have a manifold like this, and I have these 2 points, because it is a curved surface, so okay, maybe I use another example. So let's consider a sphere in R3 space, and the 2 points, North Pole and South Pole, and the geodesic between them is not the straight line between them, because this line does not lie on the manifold. It does not lie on the sphere. So the geodesic, or a geodesic, is the great circle line is this or this. Every path is a geodesic. So in sphere, it might be the case that there are several geodesics between 2 points, but for example, in this case, and x in here, y in here, the geodesic between them is just this line. You cannot say this, because this is obviously longer. Okay, so geodesically is the notion of shortest path between 2 points. But why should we why we need this notion is because in in Euclidean space, the shortest path between 2 points is the straight line. But it is not the case in a general manifold. So we need a so-called geodesic to connect 2 points, and in a sense that this path lies on the manifold, and this path is the shortest path between these 2 points. Okay, so after knowing what is geodesic, we can finally see what is exponential map. So as I just mentioned, a exponential map is a map that map vectors from tangent spaces to elements to points on the manifold. And in what sense? In the sense that this exponential map Sx of TV is a geodesic. So what does it mean? So it basically means that this point is x, and this is the tangent plane Txm. If we take this v, and if this point is exponential p, exponential x v, then this curve, okay, I change it color. This curve, parametrized by this, is a geodesic between these 2 points. So this means exponential map must walk along geodesic. You cannot say, okay, I I do things like this. You cannot say I do things like this and say this point is exponential xv because it is obviously not a geodesic. So exponential map is a has a good property that this one is geodesic. So we have the two main components.
Sorry, can I ask a question?
Yeah, sure.
So in the previous slide, so this t should be between 0 and 1.
Sorry? Yeah.
Okay,
You're right.
so
You're right.
the parameter
yes.
t goes from 0 to 1. I see. And I also have another question. So when you say shortest path, so to make sense of shortest path, we need some measure of the length of the path, right? And what is that measure?
Yeah, you ask a very great question because now we are we are in the settings of M. M is the subset of M Rm. So we can naively choose the norm or the metric, the natural metric. But as I mentioned, if we, so I jump back to here. So as I mentioned, we actually, to define a abstract manifold, we don't need to assume M the set to be in some be some subsets in Euclidean space. It can be any set. Only if we provide we say that we give it a topology, so it is a topological space. And if this topological space is locally, locally homeomorphic to Rm, then we can say this topological space is an n-dimensional abstract manifold. So in this sense, in M, we don't have so-called shortest path because what we have is a lot of open sets just as its topology gives. So what is shortest? It is induced from this Riemannian metric. So we can define such things given. So I just write in here. So then, so given x, y in this manifold, we can define and a path connected them. So a path gamma connected x and y. The length of this curve, this path. Well, okay, so gamma is from 0, 1 to m. The length of this path or this curve is defined as follows. So this is actually so this is maybe I should draw another picture here. Wait. Oh, I cannot. Okay. So what it means is I have a manifold M, and I have 2 points x and y, and I have a path from x to y called gamma. And what is the length of this gamma is because we have Riemannian metric, which means at each point on this path we have a okay, I change the color. We have a tangent spaces, and this one this gamma prime of t is a vector on tangent spaces of gamma of t. So at t equals to 0, this is a gamma prime of 0 that belongs to this tangent space, and at say t equals to 1/2. So this point is gamma of 1/2, and this tangent space is T of gamma of 1/2, tangent space of T of gamma of 1/2, and there is a T gamma prime. This is gamma prime of 1/2 that belongs to this tangent plane. So at for T from 0 to 1, we have this gamma prime of T belongs to its tangent plane, tangent plane of gamma T. And notice that we have Riemannian metric on each point gamma T. So what is this? This is a norm induced by the Riemannian metric. So,
I see. I think I understand your point. So it's basically using the differential Riemannian matrix.
Yes.
So does it mean that geodesics are defined only on Riemannian manifolds?
Pardon?
So are the geodesics only defined on Riemannian manifolds?
No.
Because this definition seems to require some sort of metric, and I think if we have a metric, we can.
I would say it is a one way to define geodesic, because if you have, for example, if you have a space that equipped with metric, then you can have a shortest path. And in a sense of geodesic, if you want to define geodesic on Riemannian manifold, you need to use this method to define. But there's other definition of geodesics.
I see. Thank you.
Welcome. Okay, so here now we are in a position to introduce the Riemannian gradient descent. Is basically we choose a direction which is gradient f, just as what we do in the Euclidean space case. We choose a direction and multiply it by a step size and negative and -1, and we walk along this direction. And how to walk is use this exponential map at xt. So okay, so here's already a picture, but I prefer for another. So if I have a point xt here, and it has a tangent plane xt, and we can find a vector gradient f at xt, and we say it is multiply minus eta t. Oh, sorry. So here is t minus eta t times gradient f, and we then update our next point via the exponential map. Okay, so I just write it. So this is how Riemannian gradient descent do. Okay, so okay, so does anyone have problems?
Okay. Since you're asking if there is any problem, I can see that you are formulating all of these based on the Riemann manifold and so on. And I'm not that familiar with that, but I'm just curious. How do you it seems like in the previous slides you have mentioned about defining some kind of an inner product.
Yes.
I'm just curious how this kind of inner product can be can lead to a metric in on this manifold.
Okay, so I search for spaces. Okay,
Because the inner product is defined at each point x, at each local coordinates for each point x, and I don't know how this can lead to a metric in this whole manifold.
Yes. So given 2 points x and y in M, and a path connected them, gamma. So this is gamma, and we may have several gamma. So so like gamma 1 and gamma 2 and the gamma 3, and the distance between them is defined as the increment of such gamma's length. Okay, I said length of gamma. The gamma connected x and y. And what is length of gamma? Length of gamma. The length of gamma utilize the Riemannian metric. So can draw this picture. So if I okay, so let's say I have this gamma is the path connected them. So what is the length of gamma? Is of the form of this. Oh, sorry. And what this norm is actually is exactly this one, this Riemannian metric on gamma t. So so at every point, so so gamma is from 0, 1 to m, and this path. So for every t from 0 to 1, there is a corresponding point on the manifold, right? So say gamma t belongs to m, and this point has a tangent spaces. So t, and in this tangent spaces, there is a specific vector called gamma prime of t. So gamma prime of t is actually a vector in the tangent spaces. So we can measure gamma prime of t's length by calculate. Sorry, this is actually by the inner product on this tangent space, because we can define norm via inner products. So through this way, we will have every point norm, and we integrated, and this becomes the length of this path. And when we choose the shortest path and say this path, the length of this path is the distance between x and y.
Okay, I can get it. It seems clear now. Okay, thank you.
You're welcome. Any problem? Okay, so I continue to. So at this point, we have Riemannian gradient descent. So we have a algorithm that works on problems of optimization on manifold problems. But we next to give a brief analysis or the results of convergence rate, which I won't prove because it involves more advanced stuff. But first, let us do a analogous to classical convex optimization settings. So as I mentioned earlier, we have convex, we have smoothness, we have strongly convex, convexity, smoothness, and strong convexity as a important properties or function classes that convex optimization considered. So we can define geodesic convexity. In what sense? So recall that convexity means for every 2 points x and y belongs to Rn. So convexity means f of y greater or equal than f of x plus a gradient of f of x. and the inner part of the gradient of f of x and the y minus x. So what we're gonna do is just replace this and this to Euclidean setting. So you can see this become this. Sorry. No, this one. So the gradient of f in Euclidean sense is replaced by the gradient of f in manifold sense, and y minus x is the inverse map of exponential f, exponential x, and of y. So let me draw this. So x, we have a exponential map that maps. Okay, maybe I write it down. Exponential x is a map that maps f of that maps vectors on tangent space to manifolds. Then its inverse function, suppose it is well defined and it exists, is map a point on manifold to its tangent vector. So it is like this. It is like this. So I have an x and I have a y, and I look. This is tangent space of x. So I basically the inverse of exponential map is just map this point back to map this point back to this vector, and yes. Okay, so this is the inverse map, and we suppose it is well defined and it exists, but in some thorny case it does not exist. Okay, so this is so-called geodesic convexity. So, and we also have geodesic smoothness and geodesic mu-strong convexity. So the basic idea is, okay, sorry, is just replace a gradient f in Euclidean sense to gradient of f of x in manifold sense, and then replace y minus x to this quantity, and other things remain the same. And you might be curious about why it is called geodesic convexity and geodesic smoothness. It is because we actually use the information of geodesic in here, because we say exponential map is a map that, okay, I draw in here, a map that, so it's x t x n, that maps a vector in the tangent spaces to a point in the point in a manifold v in the sense that the point and the x and the exponential x of v, there is a exponential there is a geodesic between them. So we actually look this geodesic to recover the original vector v in the tangent plane. And another another argument is that there's another way to define geodesic convexity, and I forgot to put it down, so I write it down. So okay, so I'm sorry, I forgot convexity. We have another definition. We have another definition for convexity. Is x y it belongs to Rm, and it is convexity in the Euclidean sense. We have this. Okay, that's less than equal to alpha of f. The convex combination of I check. Okay, greater than. Okay, so it is another definition for convexity, and it is it is equivalent to the definition we defined, the definition we offered earlier. So in Euclidean sense, in geodesic sense, I write G convex. It is more it is used in this field papers. So they all write G convex rather than geodesic convexity or geodesically convex because it is long. So G convex can also be defined this way. Oh, sorry. Alpha belongs to 0 and 1. So here the same. X, Y belongs to M, and gamma is a geodesic connected X and Y, and alpha belongs to 0 and 1. So the intuition is that in the Euclidean space, we how do we check whether a function is convex or not? We draw the function out, we draw the function, and we check every point x and y to check that if the linear combination of the function value right hand side, this is right hand side, whether it is greater than the left hand side. If for every x and y these things hold, then we say this f is convex. So in the Euclidean in the manifold case, we replace this quantity, the linear combination of x and y minus the convex combination between x and y, replace this by the geodesic. So what does it mean? Because this is x, y, the point lies on the line, sorry, a straight line between these 2 points. So this is say this point. So but in manifold we don't have straight line. So instead we use the geodesic to replace it. So it is why here we write gamma of alpha, and the right hand side is this. So which can be, think of this, it is equivalent to f compose gamma is convex. So via this definition, we can have this more elegant definition for convexity, because what does it mean for a function f defined on a manifold to be convex? It means that if we walk through if we walk through a geodesic, which is the straight line in manifold, if we walk through the geodesic and see the function value, if we behave like a convex function in a Euclidean sense, then we say it is convex in manifold or geodesically convex. So I think it is a more elegant definition, but I forget to write it down. So this is why this is called the property. The property is called geodesic convex, and similarly, geodesic L smoothness and geodesically mu strongly convex, mu strong convexity can be argued in the same way, in a similar way. So finally, let's see a simple example. Is that consider a function f of capital X, and this capital X is defined on a positive definite matrices. So positive definite, and this is matrices, and this objective function log of determinant of X is actually concave in Euclidean sense. Is that X sorry, I should write x alpha x plus e gen alpha 1 minus alpha y greater than, because this is smaller than, is greater than the linear combination of blah 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 blah. But in this sense, it is a concave. But while when we choose a proper manifold and a proper Riemannian metric, we can see it is actually geodesically convex. Okay, so oh, okay, so there is an so here is a simple example. I don't want to talk more about this because it involves more settings. And finally, we end up with the convergence rate result of RGD Riemannian gradient descent on like geodesic convex function or geodesic smooth function. So for convex and smooth, G convex and G smooth function, the RGD with step size, this step size has a rate T 1 over T, which is the case that Euclidean case. In Euclidean case, the optimization problem with convex objective function, the convex smooth objective function also has this rate O of T 1 over T. So it is similar. It is an analogous to Euclidean space. And for G smooth but geodesically strongly convex function, we improve the rate to a linear rate. So this is a form of linear rate. And this C is a constant that depends on the sectional curvature of M. So although the convergence rate is similar, is of similar form to the Euclidean space counterpart, it involves some new stuff which is C, and this C is can be varied from different manifolds, and the sectional curvature, which is a curvature to describe a manifold, but it is hard to define, so I won't talk about this here. So the thing, the important thing is that the geodesic convex case and traditional convex case achieve similar convergence rate. Okay, so this is my reference, and thanks for your listening. And is there any questions?
Okay, I have a question. So in optimization, sometimes we may deal with functions f which may go to infinity at some cases.
Go to what?
So in optimization, sometimes the f of x might blow up to like infinity.
Oh, yeah, yes.
And in that case, the convexity is defined in a different way. It is defined through saying that the EP of that is like convex or a convex set also. So I'm wondering if at some region the function f of x may grow up to infinity, then has such kind of cases be considered yet?
I don't know whether there is a literature about that.
Can I ask a question?
Yes.
Okay, so I wonder how practically relevant are these methods, because so I have seen examples where when you have to do constraint optimization in practice,
yes,
the more practical way to do it is to change parameterization. I mean, for example, the first example you show, of finding the eigenvalue. It's basically you just reparameterize instead of a vector, you just give a vector divided by its norm, its Euclidean norm, right? If you want to instead, let's say you want to optimize on a space of positive definite matrices, you can just often what people do, I mean, including myself, is just reparameterize this as a product of a matrix times its transpose. Let's say you have a matrix, I don't know, sigma. You know it must be positive definite. You just redefine it as another matrix A times A transpose. So then that is positive definite, and you just optimize for A, right? Without any constraint. So basically in Euclidean space. Or when you have, for example, when you assume that your matrix is orthogonal, then you just reparameterize your orthogonal matrix as the output of QR decomposition, for example. So all these methods that people do in practice, and I do as well, and I've seen this done many times. So whenever you have this kind of problem, you just reparameterize and you solve it in Euclidean space, because that's way easier than having to compute an exponential map, for example. So typically, computing this exponential map, it's so much complicated that nobody really do it in practice. So I just wonder what you think about this.
I think because we introduced the settings of optimization on manifold, so there might be some, for example, this log determinant function that is originally not convex, and after we adopt some manifold and Riemannian metric, and we can see it is actually geodesically convex, and this helps us to achieve a convergence guarantee that it really, if we want to minimize this function and on the set of this set, it really helps us to provide us a algorithm to the minimizer. But if we don't adopt this point of view, we don't view it as a manifold, we cannot have that property. I think so. So optimization manifold, I think it is useful in some cases to view it in manifold.
Okay, thanks a lot. I think we're almost out of time. If there are no more questions, let's thank Wang Quanzhen for very interesting and clear presentation with some great skills of drawing abstract concepts and showing all of us how it works. Thanks a lot. It was a very well prepared presentation. Thank you.
Thank you.
So our next seminar will be in 2 weeks. See you, everyone.
Thank you. Bye.
Thank you.
Bye.